All right, let's talk about one of the most famous and maybe most misunderstood ideas in all of science, Schrödinger's cat. It's not just some quirky science fact. It's a deep, deep mystery about the very nature of reality. And today, we're going to see if we can solve it together. So here's the question that sits at the heart of this whole thing. Can a cat, sealed in a box, really be both alive and dead simultaneously? It sounds completely ridiculous, right? But the strange rules of quantum mechanics seem to suggest that, yeah, until you look, that's exactly what's happening. So how is that even possible? So here's how we're going to tackle this mystery. First, we'll build Schrödinger's famous diabolical device. Then we'll dig into the weird quantum rules that create the paradox in the first place. After that, we'll meet the main suspects, the different solutions to the problem, and finally, we'll see why this isn't just an old thought experiment, but something that's actually shaping our future.
Okay, let's set the scene. We're going back to 1935, and our main character is the physicist Erwin Schrödinger. And here's the thing you have to get. He didn't create this experiment to explain quantum mechanics. Nope. He created it to show everyone just how bonkers he thought its implications were.
Imagine this crazy contraption. You have a single radioactive atom. It's got a 50-50 shot of decaying in the next hour. If it decays, a Geiger counter clicks. That click triggers a hammer, which smashes a vial of poison. And, well, you know the rest. The fate of the cat is completely tied to this tiny, random quantum event. Simple cause and effect. But the real weirdness is, what's the state of the atom before anyone peeks inside? And this is the punchline, the part so many people miss. Schrödinger himself thought this whole idea was nuts. He called the conclusion completely burlesque and absurd. He wasn't saying, look how cool quantum physics is. He was saying, look at this nonsense. If our best theory leads to a zombie cat that's both alive and dead, then there has to be something wrong with the theory. Okay, so Schrödinger thought it was absurd. Why does the math of quantum mechanics even suggest it? Well, to get to the bottom of that, we have to look at two fundamental rules of the quantum world. And these two rules, they just don't play nicely together. This is where the real conflict is. So on the one hand, there's a rule for how quantum systems behave when you're not looking. It's smooth, it's predictable, it follows the math perfectly. But then, the second you try to measure it, bam, a totally different, violent rule kicks in. Everything instantly and randomly collapses into just one single outcome. It's like the universe has two different sets of laws, one for when we're watching and one for when we're not. So that first rule, the not looking rule, leads to this mind-bending idea called superposition. It means that our little radioactive atom, before we measure it, isn't in a state of decayed or undecayed. No, it's in a weird, fuzzy combination of both states at the same time. Think of it like a spinning coin. While it's in the air, it's not heads or tails, it's a blur of both possibilities. It's a verified, real feature of the quantum world. And then there's the second rule. Wave function collapse. This is what happens when the coin finally lands. The moment you look, that blurry mix of possibilities just collapses. It snaps into one single definite reality. The atom either decayed or didn't. This is the rule that makes sure our world matches what we actually experience. You know, a world with clear, definite outcomes. And this is the million-dollar question. This is the heart of the measurement problem. What is a measurement anyway? What actually causes that collapse to happen? Is it the Geiger counter clicking? Is it the cat itself just by being a complex object? Or does it only happen when a conscious person opens the box and looks? The theory is totally silent on this. And that ambiguity is the exact weak spot that Schrödinger was poking with a giant stick. All right, so now that we've laid out the crime scene, it's time to bring in the suspects. Over the years, some of the smartest people on the planet have come up with different ways to solve this paradox. Each one is a different interpretation of quantum mechanics, and each one tells a completely different story about what's really going on inside that box. Suspect number one is the classic, the OG, the Copenhagen interpretation. This was the mainstream view for decades. It says, look, the measurement happens when the tiny quantum thing, the atom, interacts with a big, everyday classical thing, like the Geiger counter. At that point, collapse happens. End of story. So the cat was never in a mixed state. It was either alive or dead the whole time,
way before we open the box. It solves the problem by basically drawing a line in the sand between the quantum and normal worlds. The only problem? It's pretty vague about where exactly that line is.
Okay, get ready, because suspect number 2 is a wild one. This is the many worlds interpretation. It says, what if the wave function never collapses at all? What if, instead, every time there's a quantum choice to be made, the whole universe splits? So in our case, the universe splits in two. In one reality, the atom decayed and the cat is dead. But in another, perfectly real parallel universe, the atom didn't decay and the cat is alive. You split too, with one version of you seeing one outcome and another seeing the other. The paradox is gone because both things actually happened.
Then we have our third suspect, objective collapse theories. These theories say, hey, maybe the problem isn't our interpretation, maybe the original quantum theory is just missing something. The idea here is that collapse isn't caused by a measurement, it's a real physical process that just happens on its own. And the bigger an object is, the more particles it has, the faster this collapse happens. So for something absolutely massive like a cat, that alive plus dead superposition would collapse on its own in a fraction of a second. The poor cat never even had a chance to be in a weird state to begin with.
Now, there's one more piece to this puzzle that's super important. It's called quantum decoherence. Now, this isn't a full-blown solution on its own, but it's a critical clue. It points out that a big, messy thing like a cat is never truly isolated. It's constantly bumping into air molecules and giving off heat. All these tiny interactions cause the weird quantum fuzziness to leak out into the environment, making it basically impossible to ever observe. It explains why we don't see zombie cats walking around, but it doesn't quite solve that final mystery of which single reality actually wins out in the end. All right, we've got our main suspects lined up, we've examined the clues, it's time for the final showdown. Let's put these solutions side by side and see what you have to believe, what price you have to pay to accept each one as the truth about reality. So, which one is it? Which explanation solves the mystery? Well, here's the crazy part, the real catch. In terms of the math that makes predictions, they all work. But the realities they describe couldn't be more different. And that's where things get really tricky. Just look at the trade-offs here. Each of these solutions forces you to give up something you probably take for granted. With Copenhagen, you get a practical theory, but you have to accept this blurry, arbitrary wall between the quantum and classical worlds. With many worlds, you get elegant rules, but the price is, well, an infinite number of parallel universes you can never see. And with objective collapse, you get one reality, but you have to believe in new physics that we haven't actually proven yet. There's no free lunch. To solve the paradox, you have to sacrifice a piece of your intuition about how the world works.
But you know what's amazing? This whole thing is no longer just some abstract debate for philosophers. This weird, century-old puzzle about a cat in a box is now front and center in some of the most advanced technology on Earth. That's right. In labs all over the planet, physicists are now creating what they call Schrödinger's kittens. Now don't worry, they're not actual kittens. They're these tiny objects, things bigger than an atom but smaller than a cat, like a vibrating speck of dust. And they are actually putting these things into a state of superposition, being in two places or two states at once. They're literally probing that fuzzy line between the quantum and the classical world that Schrödinger pointed out. So why can't we do this with a real cat? Well, it all comes down to this absolutely insane number. A cat has more than 10 to the power of 23 particles. That's a 1 with 23 zeros after it. 100,000 billion atoms. Every single one of them is interacting with the world around it. Because of decoherence, any quantum superposition would be wiped out in a time so short it makes a nanosecond look like an eternity. It's just not going to happen. And this is where it all comes home to roost. This is why it matters today. Quantum computing. The very heart of a quantum computer, the qubit, has to exist in that fragile state of superposition to do its magic. And what's the single biggest challenge for every engineer building one? Fighting off decoherence. It's stopping the environment from measuring the qubit and destroying its quantumness. That abstract philosophical problem of the cat is now the #1 practical engineering challenge of our time.
So we end up back where we started, but now the question is really for you. Schrödinger's paradox didn't show a flaw in quantum mechanics. It showed a flaw in our common sense picture of the world. To solve it, you have to make a choice. Do you accept a blurry line between worlds, an infinity of parallel universes, or brand new laws of physics? Each path resolves the paradox, but each one redefines reality itself. The only question left is, which reality do you choose?